So this is Doug Kraft. The talk today is about the Marsh Transect model, which is meant to be a rapid screening tool that lets you assess the long-term marsh evolution in a pretty quick simulation time. So we've had a number of folks at ERDIC help out on different aspects of this project, but the big names helping out here are Rachel Bain, Richard Stiles, Candice Pearson, and Joe Golani. And it also builds heavily off of the work of our collaborators in academia, Matt Kerwin and Kendall Valentine at the Virginia Institute of Marine Science. As Tanya mentioned, this has been funded by a number of sources, but predominantly by Doer. Next slide, please. Okay, so the Marsh Transect model is really a modification of models that were described in Kerwin et al. 2016 and in the upcoming Valentine et al., which is in preparation. And these models simulate marsh evolution by looking at the edge erosion, elevation changes within the marsh, and migration due to sea level rise where that's available. The semi-empirical predictions that it makes are well suited for decadal scale estimates of coastal marsh extent, and that can be helpful to determine things such as the viability of coastal marsh persistence at a given location, the structures that may be required to maintain a certain extent and elevation of coastal marsh, as well as the characteristics of that marsh at some point in the future, which can have an influence on the ability to reduce erosion and storm surge. And then finally, it may have some utility estimating maintenance needs required to maintain a certain amount of coastal marsh. The talk today is laid out in three main sections. So first, I'll spend a few moments talking about the framework of the model, then go through the main simulated processes, and then Rachel will finish the talk with the new and improved user interface and some example simulations. Next slide, please. Okay, so the framework of the model is a 1D transect. There are three distinct regions of the domain. On the left of the domain, there is a bay, which is a uniform depth, and it's where wind or wave forcing gets applied and erodes the edge of the marsh. The marsh is to the right of that and has varying elevations and has a varying spatial extent over the course of the simulation. Then to the right of the marsh, there can be an upland, which is the area that's past the highest point of plant growth. So it will be static until the marsh migrates into that area and can begin to grow, simulating marsh migration with relative sea level rise. The actual predictions are working with a few different characteristics in each cell throughout the marsh. And within each cell, the elevation at each time step, as well as the sediment that gets deposited and below ground biomass that grows, are tracked for each time step. So the cohort from each time step, you could think of kind of stacking up to form the elevation that gets predicted for that time. And then additionally, the marsh edge is tracked through time. So wave or wind forcing pushes the marsh edge further and further back as the simulation progresses. Next slide, please. Thanks. So this is a kind of flow chart of going from the input through the different processes of the model to the output. So we can accept things like the elevation transect that you're interested in, information about how below-ground biomass grows in the marsh, the suspended sediment concentrations in the bay and other site characteristics, the bulk wave characteristics that are eroding the edge of the marsh, information about tidal datums, and a relative sea level rise that will be impacting the marsh. So with those, each of these processes gets applied within each time step, and then it cycles through as many times as it needs to come back with predictions of elevations throughout high or low marsh, predictions of the retreat of the marsh edge, as well as information about the below-ground biomass throughout the domain and marsh migration where it's able to. The processes that are simulated are sediment suspension and edge erosion out in the bay. And then within the marsh, sediment gets deposited and below-ground biomass grows. And then that below-ground biomass can decompose and sea level rises, changing the reference datums throughout the domain. Next slide, please. Okay, so I've put together one quick slide about each of the key processes. So we will start with marsh edge erosion. So it is by default a function of wave energy flux. And that default relationship is a simple coefficient BE multiplied by the wave energy flux to give you an edge erosion rate. The wave energy flux can be determined using a wind speed and fetch, or a wave height and period, or input directly as a wave energy flux. Additionally, there is the capability to specify a unique relationship between a number of variables and edge erosion for more advanced users. Next slide, please. Thanks. So also out in the bay, sediment is suspended. So this sediment suspension is related to shear stress. And again, that can either be input directly as a shear stress, or can be determined from a wave height and period, or can be determined from a wind speed and fetch. And there are a few other parameters that tune how much sediment a particular shear stress suspends. That gets added to a reference concentration that's in the bay, and then that determines what the highest concentration sediment in the marsh can be. Then with distance into the marsh, suspended sediment concentrations decay exponentially. Next slide, please. Okay, so once sediment gets suspended and it enters the marsh, it then deposits. So the way that sediment deposition is handled is that a representative tidal cycle is applied over the full time step, and that gets broken into a discrete number of points along the tidal inundation curve. And the amount of time that each point in the marsh and the suspended sediment concentration at that point directly determine how much sediment can deposit there. So I think that's good on this slide. Next one, please. Okay, so as I mentioned, the amount of sediment that deposits in any given cell is related to the amount of time that that cell is submerged. So many sites aren't well represented by a single mean high or high water reference. So to accommodate that, the model can accept an arbitrary number of tidal amplitudes, and it will stitch together different simulations for each input tidal amplitude within each time step. And what that allows is for each point in the marsh to be submerged for a more realistic duration within the representative tidal cycle. And that directly impacts the amount of sediment that can deposit in each cell. So next slide, please. So the other way that the marsh gains elevation is through below-ground biomass growth, which by default is a parabolic function of depth below mean high water. So the simplest way to specify that is with a maximum depth below mean high water where below-ground biomass stops growing, and a minimum depth or peak elevation where you no longer have plant growth. And then the point of peak growth by default will be between those two. But you do have the capacity to input your own function between those two references. Next slide, please. So additionally, if you think about a single parabola representing one plant community, you could add as many as you want above or below that to represent different populations of plants. Additionally, marsh migration as sea level rises or community switching between, say, a low marsh and high marsh community is stimulated by changing the reference as relative sea level rises, so the marsh can migrate into upland and lower communities can migrate to areas that were previously occupied by higher marsh communities. Next slide, please. So the last process which impacts marsh elevation is decomposition. The below-ground biomass that has grown during all of the previous time steps will decompose as a function of depth within each subsequent time step. So that decomposition decays exponentially with depth, and the fraction of the below-ground biomass that's left will be determined by that equation, where its maximum is a specified fraction, which has a default value of 0.1. So that would mean that at most 10% of the below-ground biomass in each cohort decomposes within each 1-year time step. And then the elevations of each cohort get reduced as the below-ground biomass decomposes. Next slide, please. So the last thing to know before running a simulation are the initial conditions. And in those, there are two distinct cases. So either we don't know what the elevations are in the marsh when we start, or we do. If we don't, then an auxiliary spin-up function generates elevations throughout the marsh and starting distributions of organic material which come up when you are looking at how much you should decompose each cell within the marsh. The auxiliary CIRP function starts with a shallow planar slope and runs a long simulation of sediment deposition and below-ground biomass growth and decomposition until the mean higher water level is at the back of the simulated marsh. And then the time span that you care about would start using that pretty stable simulation that is developed. If you do know the elevations that you want, then you can directly specify that, but then you have to apply a single fraction of that underlying material that is organic. And it will just follow the same shape as the input transect. So next slide, please. Last thing that I want to say is the big output from the model is this comparison of the starting elevation to the final elevation. And as a quick note, to avoid double counting, the reference datum within the elevations that get output don't shift with sea level rise. So if you are interpreting results, you would need to apply the sea level rise to future elevations yourself. That's this part of the talk, so I will pass it over to Rachel for the next part.
Hey, this is Rachel. Can everybody hear me? Okay, so I think we're having audio issues.
You're fine.
All right, we've got a thumbs up from Cody. Okay, so the remainder of this presentation is going to be sort of a tutorial style example of how the Marsh Transect model is run on a very practical level. So the most important thing that we want to emphasize is that we designed this tool to be simple for you as a user. Now, to be clear, that should not be taken to imply that the underlying calculations are oversimplified, at least not to an extent that they aren't representing the relevant processes. So what Doug has already walked us through is that the underlying theory and how the computations are performed. And what you should absolutely take away from Doug's presentation is the level of complexity and the broad range of physical processes that are represented by these calculations. However, we wanted your interactions with the model to be extremely straightforward. Our hope is that literally anyone with a Windows computer should be able to use this tool. The model was originally written in MATLAB, but we've recently converted it into a standalone executable program so that you do not need a MATLAB license to actually run this model anymore. If you have a text editor on your computer and you can write a text file which lists out the model inputs, there should be no barriers to running this. So with that said, let's walk through an example of how you would do that, practically speaking. Okay. Let's start out with a one-dimensional transect across a bay and a marsh, similar to what Doug was showing previously. So I've sketched that out on this slide. You have the bay on the left and then the marsh on the right side of that profile. We'll put some actual dimensions on that in a minute. On the very far right side of your screen, you'll see an example of the text file that we're going to use to actually run the model. So each line of this text file corresponds to one model variable or parameter, and we'll walk through this line by line so you can see what's going on here. The first few lines of this file are variables related to time. So we're telling the model to spin up 25 layers of stratigraphy and then it's going to run for 15,000 days, which is 41 years, and produce output every 365 days, so every 1 year we'll get output information. Moving down the text file, our next block of parameters is related to the model geometry. So we're inputting a bay fetch of 5,000 meters in the orange box, and then in the purple box we have a bay depth of 2 meters. The initial marsh width for this example will be 1,000 meters, that's in the green box, and then we have an initial upland width of 500 meters in the blue box. Now, what you'll notice is that we haven't actually defined an initial marsh slope or an initial upland slope. Because model spin-up is enabled, remember we set the spin-up flag to 1 in the first line of this file. So because we've enabled that, the initial profile is going to use some default slope values for the profile, and then it will spin up the stratigraphy to generate a physically realistic initial elevation profile. So in terms of geometry, the simplest option is to just input these 4 variables that I have colored boxes around and let the model handle all the rest. All right, so the next block of inputs in this text file are related to the model forcing. In this example, we'll force the model with a semi-diurnal tide, which has an amplitude of 62.5 centimeters. So those values are shown in the purple box. And you'll notice that we converted the tidal period, capital P, into seconds. So all of these input values need to have specific units in order for the model to run correctly. And we've written a very detailed instruction manual, which should tell you as a user exactly what units to put these numbers in. Marsh retreat in this example will be driven by a constant wind speed of 5 meters per second, and that will act over that 5,000 meter fetch that we defined earlier. And then in this example, the relative sea level rise is going to be set to 1 millimeter per year, and that's shown in the blue box. And again, you'll note that we need to list that number in meters per second when we put that into the input file. And that's information that you could get from the instruction manual. And then finally, the sediment concentration in the bay will be 0.03 kilograms per cubic meter, and that's going to be our reference concentration at the edge of the marsh. So how much sediment is initially entering the marsh during inundation. All right, so finally, at the very bottom of the input file, we have a few parameters which are related to either erosion or vegetation growth or decay. In the interest of keeping this presentation not too long, we aren't going to describe these in detail beyond mentioning that all of these values that I've highlighted on the screen are completely optional. With the exception of the model geometry and the forcing information, literally everything else has a default value written into the model, and those default values are based on the literature. So you can make this as simple or as complicated as is required for the specific problem that you're working on. We also wanted to point out that the model has a lot of optional parameters. So I'm only showing 3 on the slide. There are a lot more. We didn't show them here just to keep things brief and simple, but this could have easily been doubled in length with all of the different options that are available. We'd encourage you to check out that user manual if you're interested in seeing in more detail what this model is capable of taking as input. Okay, so we've written our input file, and now we actually need to run the model. As I mentioned earlier, we designed this to be incredibly simple. So on the screen, you're looking at 2 instances of Windows Explorer. So over here on the left, we have the directory containing the text file, this text file here. That's the same text file that we just created on the previous slide. And then in the right instance of Windows Explorer, we have the actual model executable, so this Marsh Transect model is our actual executable function. So that executable is going to be installed somewhere on your local machine. For me, it was in the program files directory. And what we're going to do is just click on our text file on the left and then drag and drop it on top of the executable on the right. And voila, just like that, the model is running. The example that we've been looking at ran in less than a minute on my laptop. And some of the more complicated examples that Doug and I have tested took maybe up to 5 minutes or so. But overall, this should be really easy to run. You just drag and drop, and you should have your results very quickly. All right, so once the model finishes running, we'll show you just an example of what the output would look like. So all of the output is going to be written to a subdirectory of the directory that originally contained the input file. So on the left side of the screen, we have that original directory. Here's our input file highlighted in gray, and all of the output was written to this subdirectory, which has a very similar name to the input file and the timestamp that it ran. Then on the right side of the screen, over in this second window over here, we've actually gone into that subdirectory, and you can see a list of all of the files that the model generated. So in here we have CSV files containing marsh elevation and stratigraphy in time and space. Also the base fetch and the mean sea level through time. And then additional files containing profiles of the inorganic mineral composition, as well as the organic content of the marsh substrate at any point in space and time. Okay, so here I've opened up one of those files as an example. This is the elevation output file. And on the screen, you can see an example of what that output looks like. So each column of this CSV file corresponds to an X coordinate moving left to right along the marsh profile. And then each row of the spreadsheet corresponds to a specific moment in time. Now, since we set the output DT to 365 days, each row of the spreadsheet is a 1-year interval. So you'll remember back to how we set the bay depth to 2 meters in the input file. So each of the -2 values in this CSV output file correspond to the floor of the bay. And then as we read horizontally across a row, the sudden jump up to positive values corresponds to the position of the marsh scarp. So what you're seeing as you read across and down, there's this diagonal shape through the spreadsheet. What you're seeing is that the marsh edge or the marsh scarp is retreating backwards towards the upland through time. So we're seeing the model in this instant is predicting marsh retreat away from its initial location. All right, so the example that we just looked at was pretty much as simple as this model can get. Just to give you a taste, and again, a very brief taste, we're not going to get into every single possibility, but just a taste of some of the more advanced features. Let's walk through one more example, which is a bit more complicated. We're mostly going to keep things the same as before and just make 2 small changes. So first of all, we're going to explicitly provide the model with an initial elevation profile. And then we're also going to input more than one type of vegetation. So in this, as well as the following slides, I'm going to be showing the old input file on the left side of the screen, and then a new input file is on the right side of the screen. And we'll have those side by side so we can compare the changes. So old on the left, new on the right. Let's walk through those changes now line by line. Okay, so the first change that we made is to explicitly tell the model what the initial marsh profile is. At the top of the input file, we're going to change the spin-up flag from on to off, and that's in the green box. And then if we jump down to the model geometry, which is in the blue box, you can see the bay fetch, the BFO variable, and the bay depth, capital DB, are the same in the old example and the new example. However, remember in the previous example, we listed the marsh width, MWO, and the upland width, and both of those were single scalar values. In this new example, we've replaced that with the path to a CSV file. So this file that I have listed here is a 2-column CSV file, and the first column corresponds to the x-coordinate along the marsh, and the second column corresponds to elevation on the marsh. So if you're working on a project and you happen to have an actual measured transect across your marsh, you could store it in a CSV file and then input that specifically into the model by telling the model where to find the file. And this allows for simulations which might be tailored to a specific location of interest. And then the second change that we're going to make is to include more than one vegetation population growing on the marsh. So in the blue box towards the right side of the screen, you'll notice that these parameters Bmax, Dmin, and Dmax, which as before, all of those correspond to vegetation properties. All of those have been changed from a scalar into 2-element vectors. And the reason for the 2 elements is because we want to look at 2 different vegetation types with different growth properties. So each element in these vectors corresponds to a different type of vegetation. Just to give you a more concrete illustration of what that means, let's take a look at one of those parameters. Let's look at Dmin. So Dmin is the minimum inundation depth at which plants are going to grow relative to the high water level. So in the old example, we set Dmin to 0 meters, and I have that sketched out in this cartoon profile here. So having Dmin equals 0 meters means that the vegetation is going to grow up to the high tide line, but not above that elevation. So for our new example, which is sketched out here on the right, we now have that 2-element vector for Dmin. The first element of the vector is negative 0.18, and then the second element is negative 0.48. So here, again, we have those 2 vegetation populations, and the first type of vegetation, which I've symbolized by the neon green V shapes on the diagram, will grow as much as 18 centimeters above the high water line. Our second vegetation population, which is symbolized by the darker green squiggles, that will grow up to 48 centimeters above the high tide line. So by adding these vectors to the input file, we can now represent what is most likely a much more reasonable example where there are multiple plant types growing at different elevations on the marsh. You should also note that we aren't limited to just 2 vegetation types. These input vectors could be arbitrarily long, provided that they're all the same length. The final thing that we want to touch on briefly is that model users have the option of inputting functions for several of the parameters. Now remember, we said that we wanted this model to be extremely easy to run and simple for you as a user. With that in mind, there is absolutely no reason that you would have to input functions into the model. Anywhere this model needs a function, it already has a default expression which is based on published literature. So you can absolutely keep these calculations simple by just omitting any function expressions altogether. However, if you happen to be a marsh expert and you want to change the vegetation growth properties or the rate of erosion, you have the option to substitute a different function, and you would do that in a similar manner to what we're showing on the screen. So in this example on the screen, we've defined 2 functions for our 2 different vegetation populations, and each of these functions is defining the growth rate as a function of water depth. And again, I can't say this enough. We want to absolutely emphasize that this option is available, but it is not necessary. So if you don't understand MATLAB syntax, or maybe you don't know what your vegetation's growth properties are, you have the option of using those default values, which we pulled out of the literature. All right, so we're getting towards the end of the hour, so I'm going to wrap up the tutorial now and conclude the presentation. If you have questions about anything that Doug or I presented today, either of us would be happy to answer those questions now over WebEx or later if you want to get in touch with us. So just wrapping up what Doug presented and then what I went over. The Marsh Transect model is a tool which was designed to rapidly simulate marsh edge erosion over decadal timescales. It also shows elevation change and migration in response to wave action and or sea level rise. The inputs to this model are extremely flexible, and the model will accept a wide range of parameters, much broader than what we presented here today. And those are so that you can mimic any site-specific observations that you have for marsh studies. So we've turned this original code into what we hope is an easy-to-use executable, and that allows users to run this model without worrying about MATLAB licensing or even needing coding experience. Our hope is that anyone should be able to run this fairly easily. And then in terms of output from the model, the things that you can learn using this model might include whether or not a marsh is able to persist in a given location, what sort of structures might be necessary to maintain a marsh through time. You can also look at whether the marsh has the capacity to reduce erosion or storm surge. And finally, the tool might be useful for looking at maintenance needs to help achieve some marsh geometry that, that is desired. All right, and one final slide. So everything that we've presented today is going to be hosted on the CIRP website. If it's not up already, it should be soon. And there's also quite a bit of supporting documentation that would provide more details if you're interested in those. So Doug wrote a text note describing the underlying calculations and the theory that goes into this model, and that draft should be available online. We've also, as I mentioned, written a user guide or an instruction manual, which walks you through the nitty-gritty of how to get this up and running and what units and what the options are for input and what specifically is stored in each of those output files. And finally, our collaborators at VIM have one paper published, another in prep, and those describe the models that were sort of the impetus for building the Marsh Transect model. So I think that concludes the presentation. We're grateful for your time this afternoon,